In this video, we're going to look at some problems involving logarithms. Let's look at some of the properties. So you can pause the video if you haven't seen these before. Let's look at the definition first. So the definition for a logarithm is given right here. You can actually call this L just to make it clear here instead of Y. The log of x to base A is equal to L. And actually this L, well in this case I have Y, is an exponent. Notice here. So you can say a logarithm basically is an exponent. So if I write, say, the log of base 8 or the log of 8 to base 2 equals to 3, this is a logarithm. It means that 8 is equal to 2 to the third. 3 factors of 2 give me 8. So this right here is the logarithmic form, and this is the exponential form here. And this one here, y equal to log of x to base a, that's your logarithmic form. And that's the same thing as x equal to a to the y, or a to the l, whatever you want to call that. This exponent here is a logarithm. You can use this definition to solve log equations. We're not going to use that many of these properties here, but here are the properties. For a positive, a not equal to 1, b positive, b not equal to 1, m positive, and n positive. Here are some of the properties of logs. The log of 1 to any base a is always 0 because a to the 0 is 1. The log of a to base a is 1. It's just the exponent there. Property right here. If you have a to a power and the power has log of m to base a, that's this space and this space are the same, the answer is always going to be m. A, exponential form here, a, and r, the answer is always going to be r. If you have the log of a product, you can express that as the sum of the log of those factors. If you have the log of a fraction, you can express that as a difference of the log of the numerator and the log of the denominator with respect to that same base. If you have the log of m to a power, you can bring this exponent r as a coefficient. You can look at the rest of these as a change of base and so on. Let's go back then to this right here. Write each exponential expression as a logarithmic expression. So again, if you have the log of some number, and again, if you saw in the properties in the definitions, this is always a positive number. Can't take the log of a negative. That has to be positive. Cannot be 0. And this base is a. This is going to equal to the logarithm. I used y in the other definition. I can put L here. So that's logarithm. And that tells me that means the same thing as x equal to a to the L. So you've got the logarithmic form and the exponential form. So this one says write the exponential expression as a log. So we have it as an exponential. We want it as a log. So for part A, we write log, and x, that's the exponent. So that's the logarithm. That's going to go over here on the right. And the 7's a base. So that's going to go here. And whatever is left becomes the argument. So he's saying that the log of 15 to base 7 is equal to x. In this case, it's given as a variable. You can compute this out though using a calculator. And notice this simply means that 15 has to equal to this base taken to that power, which would give me this. So this is the answer to part A. For part B, again, we have pi to the third equal to m. So right out, we're going to log form, so we know we have a logarithm here. And the base here has to be the same as whatever the base is for the exponential form. The base is pi. So this is a pi here. The exponent, that's the log, that goes on the right over here. 3. Whatever's left becomes the argument. So again, going the other way, this expression here, or term here, m has to equal to this number, in this case pi, taken to that power. That'll give me this. And then on this one here, again, you have a log. We're going to log form from an exponential to log. So we have that. And then the base for this one is x. So this will go here. The exponent is the logarithm, that's on the right. The other expression goes here as the argument. So to check it, 12 has to equal to x to the 5th. And that's what we have here. That's the answer to part C. Okay. Write each logarithmic expression as an exponential expression. Same thing now, except now we're given it's the reverse. We're given the log. We want to go to exponential. What's pretty straightforward is simply this right here. Whatever you have here, the argument, that's x, has to equal to whatever this base is taken to that power, the logarithm. x has to be 3 to the 4th. Part B, okay, the argument, that's 5, has to equal to the base, in this case it's 6, taken to whatever this value is, that's the logarithm, this will be 2. 5 is equal to x to the 2nd. Part C, again, log form, we want exponential, take the argument, 8 has to equal to this base, 3, taken to the x. And that's your answer for those. Okay, on the next one, find the exact value of each of these. So we have log of 49 to base 7 is equal to what? So again, the log is an exponent. So basically we're asking 7 to what power gives me 49? Well, let me write it this way so it's easier to see. 7 squared is 49. So I could just put this equal to 2. Again, whenever you have it in this form, where you have this base 7 and the base over here on the right side are the same, the answer is always the exponent, because that's the log. So saying 7 squared is 49. Now this one, we're asking the log of 1 over 125 to base 5 equals to what? So we're simply saying 5 to what power? 5 to 1 power is 1 over 125. Well, we can write it this way. This is the same thing as 5 to the 3rd. And I can bring it up to the numerator. This becomes a negative 3. So we're saying the log of 5 to the negative 3 is to base 5 is what? So we're saying 5 to what power is 5 to the negative 3? Well, that's negative 3. So 5 to the negative 3 will give me 1 over 125. And again, we're using properties of logs. Notice here keep in mind that the natural log of some expression x is the same thing as the log. I'll write it this way. And this is really e. The base is e. So this is e here. And you got e here. The base is the same there. So it's always going to equal the exponent. Because we're asking e to what power gives me e to the 4th? Well, it's going to be 4. Now the next one says find the domain of the domain. So remember, for the logarithmic function, you cannot have the log of a negative or the log of 0. So in other words, whatever this is here, it has to be positive. So to find the domain, that is the permissible replacements of the variable, you simply take the argument and make it greater than 0. We want values here that'll make this positive. Then just solve it for x. That's 2x, add 1 to both sides. This is greater than 1. Divide by positive 2. So the domain is all x such that x is greater than 1/2. We can write it in interval notation this way. And this would be a domain. Anything larger than 1/2. 1/2 is not included because 1/2 will make that 0. So that's your domain. And the next one, got f of x is equal to natural log of x plus 1 over x minus 2. Well, the domain will simply be all the all the values for which x plus 1 over x minus 2 is positive, greater than 0. And you solve this just like any regular rational inequality. You plot on a number line, plot the numbers, and make the numerator 0 and the denominator 0. So the numerator 0 at -1, -1 and 1 is 0, so put -1 over here. Denominator 0 at 2, put the 2 over here. And then we look at this number line with, to the right it'd be plus infinity, to the left would be negative infinity. And then we just find the intervals in which this thing is positive. So if we pick a number larger than 2, in this interval here, to the right of 2, say pick 3. You can pick 2.5, 2.5, whatever, 2.1. Let's stay with integers. So I put 3 and 1 is positive. 3 minus 2 is positive. Positive over positive, that's positive. So this is going to work. Between -1 and 2, let's pick 0 here. 0, 0, give me a 1 over a -2. That's a -1/2. That's not going to work. So we stay away from those numbers. And if I pick a number less than -1, say -2. -2 and 1 is negative. -2 minus 2, that's negative. Negative over negative is positive. So the domain will be all numbers to the left of -1 or to the right of 2. So for the domain, I simply write it this way. It goes from -infinity to -1. So -infinity is an interval notation to -1. And then I put a union, everything larger than 2. Notice I put parentheses on the numbers because the -1 and the 2 are not included. So it's going to go like this. So that's your domain for part B. Now for this one here, we're looking at a graph. Okay, this is understood to be base 10 here. Base 10 here. So if you have the log to base 10 or base 7, as long as the base is larger than 1, the graph is going to pass through 1, 0, and it's going to go like this. Now the fact that we have x plus 3, it's going to be the same graph. It's going to be the same graph, except it's going to move over 3 units to the left. So in other words, the graph, I wanted the domain for this one. X plus 3 would have to be greater than 0, which means x would have to be greater than -3. So the graph would have to be to the right of -3. And instead of having this type of graph, has a vertical asymptote, which is the y-axis, which is x equals 0. So all what happens here is this moves over. There's 1 there, and 2 here, a -1 there, -2 here, and right here at -3, we have a vertical asymptote. And notice that -2 and 3 is a 1. The log of 1 to base 10 is 0 because 10 to the 0 is 1. So instead of the graph passing there, it shifts over 3 units, so the graph is going like this. It approaches the vertical asymptote of x equal -3 here, passes through -2, 0, and then it goes up. That's your graph for the first one. Okay, so for this one, on the next one, same sort of thing as this one, except this is x minus 2, so this is going to move over 2 units to the right. So instead of having a vertical asymptote at, again, this is base E here. So that's larger than 1. So again, the graph is going to go up. But in this case, instead of having a vertical asymptote at x equals 0, the y-axis, it moves over 2 units. And instead of passing through the point 1, 0, now this is, if this is 3, 3 minus 2 is 1, log of 1 is 0, so it passes through this point right here. And the -3 just moves it down 3 units. Somewhere over here. And this is going like that. And that's what the graph of that looks like. Clear this. Next one we have equations to solve. Solve the first one here. Natural log of e to base to exponent of 2 to the x. This is though e here. This base and this base the same. The answer is always the exponent 2x. That's one of your properties or logs. Hopefully you stopped the video or paused the video and looked at those. This is going to be 10. Divide by 2. I get x equal to 5. This one we're simply going to use the definition of logarithm. We have the log of x minus 2 to base 4 equal to 2. We want to find x. So by definition, whatever this is, in this case x minus 2, that has to equal to this base right there, which is 4, taken to the second power. So that's going to be x minus 2. 4 squared is 16. Add 2 to both sides. We got x over here. And then 16 and 2 is 18. Now you can check these. Let's check the b here. If I put an 18 right there where the x is, 18 minus 6. Oh, sorry, 18 minus 2 is 16. And let's see, does that check? That means that 16 would have to equal 4 squared. It does. And those are the solutions. Thanks for watching. We'll see you next time.